Yeah, thank you. Thank you. Thank you, everyone. So, hello, everyone. Thanks for joining our session, Quickstart for a Breach. My name is Yossi and with me is Katchinskiy. We both work at Microsoft in the research team of Microsoft Defender for Cloud. And let's start. So, let's talk about misconfigurations. So in the past, many cloud-native applications weren't secured by default, and in general, security wasn't always a first priority when it came to cloud-native applications. And let's see some examples of it. So the first example is Helm, the package manager in Kubernetes, which we are going to discuss about shortly. In its earlier versions, Helm came with a server-side component called Tiller, and this component had permissive cluster-wide permissions in order to manage the various deployments of the cluster and other resources. So the problem was that Tiller didn't enforce authentication. So any pod in the cluster could talk to it. So even if an attacker got a limited access to the cluster, they could use Tiller to take full control. And it was a serious risk, and that's why Tiller was eventually deprecated in the next versions of Helm. Another known example is the Kubernetes dashboard. It's the old Kubernetes dashboard, which was a web interface to manage the clusters. Depends on the exact version of the dashboard. There were a few, but depends on the version. Sometimes it came without any authentication. And also in this case, once you had initial access in the cluster, you could use the dashboard for privilege escalation. And in some cases, user even exposed the dashboard to the internet, which really helped to the attackers. And the last example is Kubeflow. Kubeflow is a very popular framework for building ML pipelines in Kubernetes. And here also, in the past, installation of this framework didn't include built-in authentication. And we saw quite many instances of Kubeflow that were exposed to the internet and were quickly exploited. It includes a very large-scale campaign that targeted Kubeflow that we observed. And what's common for to all of these examples is that, from one hand, they operated with very high privileges, and on the other hand, they didn't offer built-in authentication. And workloads owners were basically only one mistake from being compromised. And here are some screenshots of blogs and reports about misconfigurations that were exploited. So, with no doubt, cloud-native applications became more secure over the years. And the example that we saw before don't really apply anymore. But apparently, such issues still exist. And what if I told you that you can still find even more severe cases? You can find applications that are completely exploitable, even with zero mistakes from the user side. Workloads that can be exploited just by installing them with the default configurations. And this is our focus for today. Cloud-native applications that are misconfigured out of the box. And this will be the agenda for today. We will start with a quick overview of Kubernetes services and Helm charts, just to put everyone on the same page. Then we will discuss about one of our findings that actually initiated the research on default misconfigurations. We will discuss about open source code scanner that we developed in our team to identify misconfigurations, and we will share, of course, what we found. And then we will share some statistics, and we'll talk about mitigations and detections. So before we deep dive into the research itself, let's just have a brief overview of some basic Kubernetes terms, just to ensure that we are all aligned. And we will start with Kubernetes services. So Kubernetes service gives us three main things. First, it gives us a stable and consistent way to access our application, even if containers have restarted or have scaled up and down. It's like a permanent front door for the application. Second, workload usually have multiple instances. For example, if we have a web application, it can have 3 or 4 instances. And Kubernetes service will spread the traffic between those instances, and will act as a load balancer. And lastly, as we're going to see shortly, Kubernetes service give us multiple ways to expose our applications. So let's start with the most basic type of service in Kubernetes, which is cluster IP. This service type assigns a virtual IP that's only accessible within the cluster. So if 2 containers in the same cluster need to communicate with each other internally, that's what we're going to use. Another type of service is node port. node port opens a static port on every node in the cluster, which means your service is now reachable from outside the cluster. And if the networking rules of the node will allow this traffic, so your application will be exposed. And finally, we have load balancer service. And this is the most common way to expose applications to the internet in managed Kubernetes services, like AKS in Azure or GKE in Google. It automatically assigns a public IP that exposes the application using a load balancer that is managed by the cloud provider. Vast majority of attacks that we see in Kubernetes are against workloads that are exposed in this way. And there are some more ways to expose applications, but that's enough for now. Another topic that we want to go through very briefly is Helm. Helm is a very popular way to deploy cloud-native applications in Kubernetes. Helm is a package manager for Kubernetes, and it works with charts, which are a set of Kubernetes configuration files which are reusable and versioned. When you install a Helm chart, the configuration files are deployed to your cluster, and Helm charts come with default configurations, and users can override them if they need to. And that's what's important for us. The last point that we talked about. Helm chart come with default values, which are the default settings of the deployment as the maintainer configured them. Unless you don't overwrite it explicitly, that's going to be the configuration of your workload. And sometimes these configurations have surprises. So after all of this background, let's dive into our main topic of the session, which is default misconfigurations. So let's share our recent findings. So how exploitable misconfigurations are created? Usually it's a combination of two things. The first is exposure to the internet, and second, weak or non-existing authentication. So let's start. Here is the first default misconfiguration that we discovered and initiated the whole research. In late 2024, we identified suspicious network activity on multiple Kubernetes clusters. In the same time, it was in the exact same time. And the activity was also identical, so we understood that there is a connection between the clusters. And what we found is that they are all running Apache Pinot. Apache Pinot is a data store that is used for low latency analytics and for querying in real time. So we said, okay, interesting. We dived into it, and what we saw is that all of those clusters exposed the controller of Apache Pinot externally to the internet by a load balancer. The controller is the brain of the framework. It handles tables, schema, and does the overall orchestration. So it makes sense that if someone got access to the controller, they can take full control of the application. But the question is, why so many clusters expose it? And even if it's exposed, how attackers can take advantage of it? So let's talk about how you deploy Apache Pinot in Kubernetes. In their documentation, Apache Pinot referred to the Helm chart in their official GitHub repo. And let's see what happens when you install the Helm chart with the out-of-the-box settings. So as you can see here in the picture, we get two load balancer services. One for the controller that we just talked about, and other one for the broker, which is a component that handles the queries. That's, by the way, the section from the Helm chart that is in charge of this exposure. And as you can see here, if you don't explicitly disable it, the Helm chart will deploy a load balancer service. And the amazing part is that there is no default authentication mechanism. So if you use the official Helm chart with the default configuration, you simply open your data store to everyone in the internet. And here you can see the controller dashboard. You can control the application, you can query the data, and you can basically do whatever you want. And that's exactly the pattern that we saw. Exposure to the internet plus weak or non-existing authentication. So what can we learn from this case? First, default misconfigurations are still a thing today in 2025. Still, there are popular applications that come severely insecure by default. And second, detecting those issues at scale is hard. Understanding the configuration of each and every workload is difficult. And if you are managing hundreds of applications across multiple Kubernetes clusters, it's challenging to always identify such cases when they occur. Now to you, Michael.
Okay, thank you, Yossi. So, just a second. Okay, so at this point I had a choice. I could either sit down and finish the blog post about Apache Peanut like a responsible adult, or I could go down the rabbit hole and start digging through GitHub to find more Helm charts that does the same thing. And well, you can probably guess what was my decision. So I decided to scale up the hunt. I started scanning for both GitHub and Artifact Hub for YAMLs, Helm charts, and anything else that might expose a cluster. I also, So I also filtered manifests that expose the node port and load balancer, which are the ones that actually expose the applications in the wild. I sorted the results by their popularity, meaning by the number of stars in the repo. And finally, I deployed the most interesting ones just to validate exposure and the behavior that we anticipated. So at first I took a naive approach. I tried finding all of the YAMLs that expose a load balancer service. And apparently you cannot directly sort how popular is the repo by the number of stars using the GitHub code search. So it was practically impossible to handle such amounts. So next I changed my method. So I started, instead of scanning random YAMLs, I focused on Helm charts because, as we said, this is the popular way to deploy applications. So I searched inside the values.yaml file, which contains the default configuration, as Yossi just said, and I removed some tutorial and learning projects just to get the trash out of it and focus on real-world examples, but there was still a problem. We got many results, and GitHub code search allows you only to get up to 1,000 results per search. So to get around that limit, I had to get creative, and I split my GitHub search into smaller chunks, okay? So for example, one thing that I did is to filter results based on port numbers. So instead of one big search, I created 10 smaller searches, one search for ports starting with the digit number 1, and one search for ports that starts with the digit 2, and so on. That way I collected a lot more results. And finally, we scanned over 12,000 files belonging to 6,700 unique repos. And I deployed manually over 300 shards that all of them had at least 500 stars. So among the findings, several charts still included the hard-coded password just baked into the values.yaml file, as we mentioned, that contains the default configuration. Some applications were exposed with no authentication at all, even not a minimal authentication, and others surprisingly allowed us to self-register ourselves without any validation at all. So these are fundamental misconfigurations that came with some pre-configured YAML files, and even though these Helm charts are used for testing or a Quickstart or just to test something out, they still expose the cluster. So let's dive into 3 interesting use cases that we found. So the first one is Meshery, which is an open source tool that lets you manage service meshes and share it with others. And with Meshery, you get this cool drag and drop interface. And as you can see, you can create a template of resources and applications and share it with others and deploy it on the cluster. And also you can integrate the cloud account into Meshery and deploy stuff from your cloud account and integrate it to Meshery, which is kind of fun. And when you deploy Meshery on the Kubernetes cluster itself, what happens is that you can manage the resources on the cluster. It's like a Kubernetes dashboard, but much smarter. And to install Meshery, we went to the official website, and the official website says, hey, install Meshery using our Helm chart. And our GitHub scanner noticed that the Meshery application is exposed by default with a load balancer and could be accessed from outside the cluster. And when accessing the IP address, the external IP address of the Meshery services, we stumbled upon this screen and we thought to ourselves, oh well, it's not going to work. We need to be a registered user, right? But when we pressed on the sign up button, we were able to register ourselves and log into the program. And we were greeted by this beautiful screen. It contains all the information about the cluster that Meshery is deployed on. And when we navigated to the drag and drop interface, we could choose which resources we wanted to create. And in this example, I've created a pod that shares the PID namespace and the network namespace with the host. and I press deployed on the right side of the screen. And then in a couple of seconds, we can see that a new pods was created, and it was created by Mesher itself. And just to verify the scopes of the permissions that the app had, I queried the role of the application, and apparently it has full cluster admin privileges. And they also provide a CLI tool, so instead of using the Helm charts, you can use their Mesher CLI or CTL tool, which also deploys Mesher on your Kubernetes cluster, and it also exposes it on an external IP address. So it's not just a Helm chart. So just to summarize, gaining access to the Mesher dashboard effectively gives you cluster admin permissions. And when someone integrates Mesher with a cloud account, you get the permissions to the cloud account as well. So another product that we've seen is Selenium, which is widely used open source framework for browser automation and testing. And Selenium Grid lets you run tests in parallel, and it works like a smart proxy, so you run commands to different browsers. And in the past year, we've seen a lot of campaigns targeting Selenium, so there were reports from Kado Security, from Wiz, and from Aqua, the PerfCTL campaign, which also targets Selenium. And we thought to ourselves, why is Selenium being targeted? And apparently, by default, Selenium doesn't ask for any authentication at all. So we searched for charts and manifests that expose Selenium with an external IP address, and apparently we found many of them. And one was even in the official Kubernetes repo using a node port. So the official Kubernetes repo was telling you to expose Selenium externally, which doesn't require any authentication at all. And Shodan also supports the claim that Selenium is widely exposed to the internet. And apparently, to abuse the Selenium functionality, so attackers abuse the Chrome option set binary method, which is originally used to run the browser binary from an alternative location. And in the recent campaigns that we're seeing here, we saw a lesser known technique that is using a flag called utility command prefix. So attackers prepend their command before Chrome starts using this flag that I just showed you here, and they execute a file that they created beforehand, which is called, in this case, osman.css, which is a malicious bash script. It's not a CSS, as you can imagine. And interestingly, this technique was mentioned just once in 2020 about pawning Avast browsers, but we haven't seen any documentation at all, and this specific flag, it was very difficult to find it. So attackers know what they're doing. And to our last case, so Prometheus and Grafana. Prometheus is an open source monitoring system. It collects and stores matrices. So it gathers data from different applications and stores it in a time series database. And Grafana is the visualization tool. So you take data from Prometheus, you plug it into Grafana, and it makes you an interactive dashboard. And in this case, while testing the results from our GitHub scanner, we came across an interesting chart, Helm chart under the Prometheus community repo that deploys Grafana and Prometheus as well. And when we deployed it, it seemed like the password to the Grafana is stored in a Kubernetes secret. But when we created a secret, we were surprised to see that it seems like the password to the Grafana isn't such a big secret. And as expected, the values.yaml file was setting the password to prom operator. And what was interesting, though, is that there was a pull request that was waiting just to fix this issue. It was waiting to be merged. And by searching Shodan, we can find tens of thousands of exposed Prometheus and Grafana instances. And by design, Prometheus doesn't require any authentication at all because it assumes it's running on an internal network. And Grafana doesn't require authentication. But assuming we have here around 130,000 exposed Grafana dashboards, let's assume we have maybe 0.5% or 1% that are misconfigured in the way that I showed you. It's still a lot. It's still over 1,000 exposed dashboards. And we talked about applications that are exposed to the internet. But what about applications that are exposed internally? So here are a few things that you need to know very quickly about Kubernetes networking. So in Kubernetes, every pod can talk to other pod. By default, there are no firewalls, no isolation between them, and namespaces are just a fancy way to define boundaries regarding network. And without a network policy, one compromised pod can access everything, almost everything in a cluster. And to track internally exposed application using the cluster IP service, you need to know a few things. So first of all, cluster IP services have their own IP range, and it changes between Kubernetes versions, and the DNS name of the service is service_name.namespace, and it's a format that does not change. So one thing that you could do, you could brute force DNS. My mom. She always does it, I'm sorry. And it's on silent, but they're excluded from silent. So, okay. So again, we talked about cluster IP. It has its own IP range, and the DNS name is service_name.namespace. So one thing that you could do is you could brute force DNS. So you can use word lists, and with these word lists, you can find services that are exposed internally in the cluster. Another thing that you could do, you can scan the IP range and look for unique ports. So you can scan for, like, let's say, the port of Redis or the port of PostgreSQL, and in this way you can know, hey, this IP address is actually running Postgres behind it. And the final thing that you can do, which is very powerful, you can perform reverse DNS lookup to discover internal service names. And this will be able if core DNS allows it, and it does allow it on AKS and EKS. So let me just show you how it works. So assuming I breached the pod in a cluster, I wrote a script that does reverse DNS scanning to all of the IPs in the cluster. And quickly, I was able to find all of the cluster IP services that expose application inside the cluster. So I identified over here a Redis cluster, a Redis instance, and I tried to reach the port with Nmap. And as you can see, the port is open. And then I was even able to access and connect it from the breached pod, because by default, up until recently, Redis did not enforce any authentication. And another example is with the popular Elasticsearch chart from the Bitnami repo. So the security features are disabled by default, and this is a very popular repo. And again, from the breached pod, I was able to make a reverse DNS query. I found out that it's an Elasticsearch. Behind this IP, there's an Elasticsearch service. You can see it by the name. And I was quickly able to connect to this Elastic because, again, it doesn't require any authentication at all. Back to you.
Thanks, Michael. Okay, sorry, a second. All right, so let's start to wrap up what we've seen so far. So first, while cloud-native security definitely improved over the years, we can still find quite many issues, as you saw, including in popular applications. Second, what we see in real-world data is that this issue affects organizations in all sizes, from small companies to really large enterprises. As we have seen throughout the session, in some cases, the misconfigurations come out of the box. So it's not even about a mistake that somebody does. Sometimes it's just relying on the default settings. And that's why it's crucial to really understand what we deploy and not just relying on the default configurations as they come. We've seen cases in which misconfigurations were exploited in less than 10 minutes from the deployment, which is very, very quick. So it really makes this issue so dangerous. As Michael showed, also internal access could be dangerous. It's not only about initial access. Sometimes it's about privilege escalation in the cluster. And lastly, more than 50% of the attacks that we see against containerized applications originate in misconfigurations and not software vulnerabilities. So even if your organization has the best vulnerability scanner, even if you automatically block every vulnerable application in the network, still you did only half of the job. So after we talked about the problems, let's try to talk about the solutions. And we will start with mitigations. As we said, exploitable misconfigurations are usually a combination of two things: internet exposure plus weak authentication. And let's begin with the internet exposure. We should always map the external surface of the organization. Obviously, some applications should be exposed to the internet and it's fine, but sometimes this exposure is actually misconfiguration. There is an interesting pattern that we see over and over. Users sometimes manually change the service configuration from cluster IP to load balancer. Often they do it for debugging or for testing, but they just forget to change it afterwards. And you can identify such cases by monitoring the Kubernetes audit log and to see cases in which users change the service configuration. And if you see that somebody changed the service type from cluster IP to load balancer, it's something that you want to check usually. Now let's talk about authentication. In cloud-native applications, this is often configured in the application manifests. So look for problematic settings like allowing anonymous access, and also look for usage of default credentials or easy-to-guess credentials. And now with LLM, it's actually quite easy to identify easy-to-guess credentials. So if you scan your manifest with LLM, you can try to identify it. So we talked about mitigations. Let's talk about detections. And as we said before, it's difficult to have a generic rule that identifies exploitation of misconfiguration, but still we notice something interesting. So many containers have predictable activity. It's not new. Containers usually run a single application, and therefore they behave quite consistently. And turns out that most of them are very consistent. Our large-scale analysis showed that by average, containers are running 4.5 different processes, and only less than 1% of the containers are running new processes after their initial bootstrap. So by tracking the behavior of the containers, for example, by using eBPF tools, you can try to identify anomalies in the container's activity and potentially identify exploitations of misconfigurations and other threats. So we saw that default misconfigurations still happen in 2025, and we hope this session gave you some insights about the problem and some tools to mitigate the risk. Thank you very much. We'll be outside to take questions.